This is the recording for the Unit 3 practice test, Energy and Momentum. Question 1, which of the following is the largest momentum relative to Earth? Well, there's a small dog or small mass dog running down the street. There's a pickup truck speeding along a highway, a tightrope walker crossing Niagara Falls. The Mack truck is parked in the parking lot, and then there's a science building on campus. Both these here have a lot of mass, but zero velocity relative to Earth, hence no momentum relative to Earth. The dog is running, but has a small mass. The tightrope walker has a larger mass, but he's walking. And the pickup truck is speeding along, so it has appreciable mass, and it's fast. So this one has the largest momentum. Impulse-momentum relationship is a direct result of Newton's second law. You can find it in the book. Conservation of momentum is most closely related to Newton's third law. You can also find it in the book. This one is actually really important, that Newton's third law, as we learned, that the action and reaction principle, equal and opposite forces on two different objects, is the exact same thing as the conservation of momentum, just expressed in different terms. You will also see that the conservation of momentum here in this chapter is quite often applied to two different objects as they collide with each other or as they push off each other. So again, we're back to the two different objects that we used in Newton's third law. When you are in the way of a fast-moving object and can't get out of the way, for example, you might be in a tight alley and there's this cart coming at you and there's no space to go to the side. You will suffer a small force of impact if you decrease its momentum over a long time. You can try to hold on to it and just walking backwards, or you can actually run away from it and, well, hopefully it's not going to do too much damage. Padded dashboards in cars are safer in an accident than non-padded ones because an occupant hitting the dash has an increased time of impact. So the momentum, the energy that you need to get rid of is still the same, but with an increased time of impact, you decrease the force. That's the impulse in order to get rid of the momentum. So increased time means that the force is less. A ball is moving 3 meters per second, has a momentum of 48 kilograms meters per second. What's the ball's mass? 48 divided by 3 is 16, and of course with the meters per second here dividing out this one here, the correct unit is kilograms, 16 kilograms. Heavy truck and a small car rolling down a hill at the same speed are forced to stop in the same amount of time compared to the force that stops the car. The force needed to stop the truck must be greater because it says it's the same amount of time. The heavy truck has more mass, therefore it has more momentum to begin with. So in the same amount of time with the impulse, it has to have a larger force to get rid of the momentum. This one requires a calculation. Notice that there are two objects here with the conservation momentum. So a 5 kilogram fish, speed of 1 meters per second, which is the momentum of 5 kilograms meters per second. And then there is an absent-minded 1 kilogram fish at rest, which means it has a momentum of 0. Add the 2, that's still 5 plus 0 is 5. That's also the momentum after one fish swallowed the other one. That's the conservation of momentum. Now that fish, of course, has gained mass, another 1 kilogram, so 5 plus 1 is 6 kilograms. Divide the momentum, the total momentum of 5 by the mass of 6, and you come up with 5, 6, and if you do the unit analysis, you come up with meters per second, which it should be because it's a velocity or speed. Okay, a little bit harder here, 5 kilogram shark, 1 meter per second, which is still a momentum of 5 kilograms meters per second. This one here now, though, has a momentum of 4. In fact, it's a negative 4 because it's swimming towards it. So we have 5 kilograms meters per second here. We have negative 4 kilograms meters per second. Add the 2, so 5 plus negative 4 is 1. That is being conserved. So in this case, the shark, as it swallows the other fish, has a total momentum of 1 kilogram meters per second, has now a mass of 6. So it has the momentum of 1 divided by 6. I'm sorry, speed 1 divided by 6 meters per second. Almost the same problem as this one here, except that in in question 9 compared to question 8, the fish was swimming towards the shark, and therefore it slowed it down more. This one here still has 5/6, which is about 0.83. This one here has 1/6, which is about 0.17 meters per second. Right, 1 kilogram chunk of putty moving at 1 meters per second, so it has a momentum of 1 times 1 is 1. 5 kilogram bowling ball at rest, that's a momentum of 0. 1 plus 0 is 1. Divide that by the total mass after the putty has collided with the bowling ball, so 1 divided by 6 comes out to 1/6 meters per second. An ice sailcraft is stalled on a frozen lake on a windless day. A large fan blows air into the sail. If all the wind produced by the fan strikes a mountain spike from the sail, the craft will move to the right, and you will see that the explanation is written here. In order to catch a ball, a baseball player extends the hand forward before impact with the ball and then lets it ride backward in the direction of the ball's motion. Doing this reduces the force of impact on the player's hand, principally because the time of impact is increased. Ask any baseball player, they will do that. They will definitely not move their hand towards the ball. There would be really big impact. It's still almost the same amount of momentum to get rid of, but in a shorter amount of time, hence the force is going to be larger. So you really want to avoid that. Move the glove with the ball's motion. If you push an object a given distance while applying twice the force, you do twice as much work. That's because work equals force times distance. 1,000 kilogram car and 2,000 kilogram are hoisted the same distance. Raising the more massive cars requires twice as much work because, again, work equals force times distance. In this case, the force is the weight of the car because the distance is vertical. When a car is braked to stop, its kinetic energy is transformed to heat. You will find that in the book. Both a 50 kilogram sack is lifted 2 meters from the ground and a 25 kilogram 4 meters in the same time. The power expended in raising a 50 kilogram sack is the same. The way to calculate that is calculate the potential energy, 50 kilograms times 2 meters times gravity, 9.8 or around a 10 comes out to 1,000. Here it's going to be the same thing. 25 times 4 times 10 is 1,000. In the same time is still 1,000 divided by the same time, so the power is the same for both of them. TV set is pushed 2 meters with a force of 20 newtons. How much work? Work is force times distance. 20 times 2 is 40 joules. Car moves 4 times as fast as another, then compared to a slower car, the faster car has 16 times the kinetic energy because kinetic energy goes with the square of the velocity. Kinetic energy equals 1/2 mass velocity squared. Strictly speaking, more fuel is consumed by a car if an air conditioner, headlights, or even the radios turn on. This statement is almost always true. I still don't understand why the word almost is there. To me, it's really always true. Because it, of course, takes any one of these gadgets take energy from the battery. The battery is recharged by the alternator, and the alternator, of course, gets its energy from burning the fuel. That's also why on really steep hills, you're advised to turn everything off. So turn off, even if it's hot, turn off the air conditioner. I guess if it's dark, I guess leave the lights on, but turn the radio, turn everything off, because you really need all that energy to actually get up that steep slope so that it wouldn't waste energy on the alternator and the battery. The machine puts out 100 watts of power for every 1,000 watts put into it. The efficiency of the machine is 100 watts divided by 1,000 watts, which is 0.1 or 10%. Efficiency can be computed by comparing the two powers with each other or the two energies with each other. You will see that in the heat lab that we're dealing with energy rather than power. Consider hydraulic press. When the input piston is depressed 20 centimeters, the output piston is raised 1 centimeter, so it's a mechanical advantage of 20. Respectively, it doesn't go as high, but it reduces the force to 1/20th. So on the same present input force of 1 newton, therefore can lift loads up to 20 newtons. Notice I left 20 newtons out itself because it says an input force can lift loads of, well, 2, 5, 10, 15, 19. 22 obviously not. There used to be a 20 here, but that confused students. They would only check this one, overlooking that it can lift any of one of these. It doesn't have to be 20. But anything that is as large or smaller than that. If the speed of a moving object doubles, which of the following necessarily doubles as well? Well, the kinetic energy goes with the square, so that can't be it. For the acceleration, well, if you double the speed, acceleration is speed divided by time, but there is nothing written about time here, and all of the above is not applying because the momentum actually doubles when the speed of a moving object is doubled. Moving object has velocity, speed, momentum, kinetic energy. An object at rest may also have potential energy. None of the others, because all of these here would be 0 if it's at rest. A bullet has more kinetic energy than the recoiling rifle from which is fired because the force on the bullet acts over a longer distance. So kinetic energy, it gets it from the work that is being done. Work is force times distance. The force is the same on both the bullet and the recoiling rifle. That's Newton's third law. But the bullet is pushed with the force, which comes from the combustion of the gunpowder, through the length of the barrel. And so the bullet has a long way to acquire the kinetic energy, force times distance. The recoiling rifle, because it has much more mass, is actually moving just a small distance backwards. So same force for it, though, times a much smaller distance means that the recoiling rifle gets much less kinetic energy. The force that accelerates a rocket in outer space exerted on a rocket by the exhaust gases. So it pushes out the exhaust gases in one direction and gets the same amount of force in the other direction, which is Newton's third law. And the reason why it's here is it's also the conservation of momentum. By the way, I just noticed that earlier I referred to a lap on the heat engines. These efficiency equations or mechanical advantage also apply to the laps that we do in Unit 3, which is the simple machines, for example. Astronaut floating in space throws a ball as massive as herself toward her nearby spaceship. If the ball bounces back toward her without losing speed, her best choice at that time is to, well, actually what happens to her as she throws it towards the spaceship? Well, she is being recoiled backwards, same force, and she's actually getting away from the spaceship. Not good. Try to catch the ball and wait a few minutes to be rescued. Well, not a good idea because she actually might get more momentum from the ball, still going away from the spaceship. Try to catch the ball and then throw it away from the spaceship. Well, that could maybe work. However, the ball is as massive as herself, and she won't be able to catch it. It's just going to move with the same speed after it bounces off the spaceship. Forget about catching the ball, but throw a helmet towards the spaceship as well. No, that actually gets you more away from the spaceship, so this one here is her only hope. And then the remaining problems, you have these already as YouTube videos, respectively, in the worked out problems in physics. And that was the practice test for Unit 3, Energy and Momentum.